Before we start off with state machines, let me give a recap of what we did last week. We went through design patterns, what design patterns mean to us, their advantages like reusability, being heavily tested by the industry, and readable by developers through time and distance. More specifically, we learned the master-slave and producer-consumer architectures. We understood that there were architectures that help in simultaneous and independent execution of multiple processes with data communication between them. This week, we'll be discussing about the state machine architecture, what it is, why, and where it can be used. Before we start off with the session, I'd like to know how many of the attendees are familiar with the state machine architecture in LabVIEW or in any other programming language. You should be seeing a poll. It should pop up now. Just as the previous week, I'm getting a mixed response over here. Half of the attendees are familiar with state machine architecture and the other half aren't. Before we jump into state machine architecture, let's talk about something simpler. Sequential programming. Suppose there are a few pieces of code that need to run in LabVIEW, and you place them on the block diagram one after the other. A quick poll now. Will they or will they not execute one after the other? No, they do not execute one after the other because there is no dependency between them. LabVIEW treats them as parallel processes. To run them in sequence, we have to induce data flow between them. For example, by wiring the outputs of one piece of code to the input of the next. Also, in the case when errors are not as visual as here, we could use the sequence structure to artificially induce data flow or sequential structure between them. Sequence structures force sequential order into the execution. So this is sequential programming, that is programming in sequence. Until the first frame executes completely, the second frame does not start, and so on through the third and the fourth frame. Now, to understand the state machine, let's again take the top-down approach, starting with an application in mind. Have a look at this user interface. It's a simple representation of a single film ticket vendor for a film that has an entry age restriction of 8 years. There are buttons to enter the age of the customer, an entry to fill in the amount of cash given, an indicator to show if the ticket has come out, and an indicator to show how much change is returned to the customer. Now let's run it to see how it actually works. So here's the front panel of the LabVIEW BI. Now I run it. I enter the amount of cash to be paid. I click on pay. I get a prompt to enter my age. I enter 23. Click on age entered. And then I get the ticket, and then I get the change, and the state reverts to insert the amount of cash again. Now, I'd like to create this in LabVIEW. That is, I want to know how the block diagram will look like. To understand the application better, let's see a flowchart which explains the working of the ticket vending machine. There are 4 steps to it. Step 1 is to enter the amount of cash rendered by the customer. The second step is to enter the age of the customer. The third step is to indicate that a ticket has been generated. The fourth step is to indicate that the remaining change has been given out to the customer. This looks like a sequence of 4 steps. However, it's not actually as straightforward as this. There are 3 main features I'm missing in this implementation. What if I'm underage? It should not go to the next step, right? So step 2, I enter my age, and if I'm underage, it shouldn't execute step 3. So I need a condition. I need to check if the age entered is appropriate. And similarly, I need to check if the amount of cash dropped is greater or lesser than the ticket price. Also, I will need to check if there is change to be returned or not. Next, what if the customer doesn't enter the age at all? I need this step to continuously execute. That is, I need to have a continuous loop running here until the condition is met. Similarly, I need step 1 to execute continuously until the customer has rendered the required cash. The next feature I'm missing is, suppose the age entered is less than 8 years. The execution has to return to step 1. This breaks the sequence and jumps across it. After the end of all steps, the program must restart for a new ticket. This looks like there are 4 states in which the program can exist. Step 1, Step 2, Step 3, and Step 4. The program can transit from one state to another depending on some conditions. So to summarize, we have recognized 3 necessary components that need to be present in our LabVIEW BI. The first is the state functionality code. For example, the subtraction between cash dropped by the customer and the price of the ticket. Second is the state transition code. For example, the code that checks if the age entered is above 8 or not, and the code that checks if the amount given by the customer is greater than the price of the ticket or not. The third feature is to continuously check what conditions are being met and decide which state to execute next. This also forms the basic framework of the state machine architecture. So these are the 3 necessary components that need to be present in our LabVIEW BI. The state functionality is straightforward programming, and in this case it's mostly arithmetic. State transition or condition code can be implemented in a variety of ways. In this case, we'll be using the greater than, lesser than, and select VIs to implement this. The continuous checking is implemented by placing a case structure inside a while loop with cases depicted by enums and carried through iterations by shift registers. The while loop is for continuous execution. The case structure is to determine which state to execute next. The enums are used as labels for different states, and the shift registers are used to carry the enum through different iterations of the loop. For example, if I decide in the state A that the next step is still going to be A, the state information is sent through this tunnel into the shift register, the left counterpart of which generates the same enum back to the case selected terminal, and the state A executes again. Now that we know the outline of the program, let's see how to build it. First comes the state execution code. So let's see the various states of the program one by one. State 1 is cash. Here the customer pays the required amount of cash. A numeric control named amount is used to type the amount of cash given by the customer. And there's a button named pay to enter it. Also displayed is the phrase insert amount as an instruction to the customer. The state transition code here is to check if the cash drop is greater or lesser than the price of the ticket, and to wait for the pay button to be pressed. If the cash entered is greater, jump to the next step, that is age. If the cash entered is lesser, stay in the same state until the user has entered a valid value. The next step is age. A numeric control is used to type in the age of the customer, and there is a button to enter it. It also displays the instruction enter your age on the front panel. The transitional code in the age state checks if the age entered is greater than or lesser than the restriction of 8 years and waits for the OK button. Since there are 3 possible states for the next iteration, you can see there are 2 different select VIs over here. The first VI checks if the age entered is greater than 8 and chooses whether to go to the next state or to restart the entire process. The next select assumes that the customer is of the required age and checks if the customer has pressed on the age entered button. If he hasn't, this age state is repeated again. The next state is vending out the ticket. Here, the amount of change is calculated and an LED to indicate that the ticket has been given out glows. A Boolean indicator that glows when the ticket is generated. There is also a display with an instruction saying please take the ticket. The last state is change, where the amount of change calculated is given out. There's a simple instruction which says please take the change and an LED which glows to indicate that the change is vended out. Here you can see the transition code has only one state, which is to restart the entire process again. Now, we have seen the execution, the functionality, and the transitional code of different states. We have all the building blocks. Now we must create the framework for it. Now let's go to LabVIEW. To create the framework, I first create a while loop. I create a while loop on my block diagram, which is for the continuous execution, and then I create a case structure inside it. To label the states, I create an enum to represent different states of execution. For example, I enter cache, age, ticket, and change. You can see the different states of the enum. I connect the enum to the case selected terminal of the case structure, and then I add case for every value. Now you can see there are 4 states created. The next step is to create a shift register. For example, in this case, I would connect the enum to the right hand side of the while loop and then replace the tunnel with a shift register. With this, we have the basic framework on which the state machine is built. Now, all we need to do is copy the different pieces of code that we've seen earlier into different states of the case structure. After doing the exercise, the finished code will look like this. The VI is now complete, and here on the left hand side is the user interface. Using highlight execution tool, let's now observe the flow of the program. First, all the controls are reinitialized to their default values. Next, the VI waits in the cache state until I enter a valid value and hit OK. Then it goes to the state age and waits there until I enter an age above 8 and hit OK. You can see the state of age being reiterated again and again. Now, the age transits and goes into the case ticket. Here, the LED ticket glows, and then the state transits to change, and the change LED glows, and the VI reinitializes and goes back to the state cache. So we've started with an application in mind. We've gone through all the features that it requires, recognized the components of LabVIEW that can implement these features, and finally built the program in LabVIEW. However, where do we use the state machine? One very common application, as we saw before, is user interfaces, where different user interactions might execute different states. This architecture is also used in process tests, where each state represents a segment of the test. Depending on many factors, a test segment can be executed once, multiple times, or not at all. We started off with sequential programming and then went on to build a state machine. Both of them involve executing multiple pieces of code. So what are the differences between them? Sequential programming has a predefined order of execution and cannot be changed during runtime. State machine decides the order of execution programmatically depending on user inputs and previous dependencies. In sequential programming, you can neither repeat or skip states. In the state machine, both can be done based on conditions set and met. You cannot exit the program until all the states are executed in sequential programming. In state machine, you can stop the program between any two states. We've created a state machine based on a specific requirement, that is a ticket vending machine. Now let's analyze a pre-built state machine and recognize the various components in it. So the example we will be seeing is that of a weather station. Here, we measure the temperature at a constant rate. We then check if it's between min and max limits, that is upper and lower limits, and then have a warning message displayed and logged when the temperature goes out of range. So first, let me go back to LabVIEW and open the example. So here is the VI, the weather station. So let's run it. When I run it, it asks me to save the warning log text file. I save it to a location, and then, as you can see, the temperature starts getting plotted onto the temperature graph. I've set the limits of freeze and heat stroke to 20 and 30, and you can see the warning message alternating between no warning, heat stroke, and freeze warning. During the execution, the warnings are also logged into a text file. Now let's stop execution and check what the log file has. As you can see, we have logged all the temperatures which were above 30 and below 20. In this case, almost all of them were just above 30. So now we've seen the user interface. Let's analyze what is there in the block diagram, that is the functionality. Here, just like we created, there's a while loop, and inside it is a case structure with enums to represent different states. There are 4 different states: acquisition, analysis, data log, and time check. Every state will have functionality code and transitional code, which I have explicitly labeled. In the acquisition code, the functionality is just temperature generation and plotting it on the graph. The transitional code sends us directly to the analysis state. There's no real condition in this state. So the acquired temperature goes to the analysis state. Here, the functionality code compares the current temperature to an upper and lower limit and generates a warning if out of range. The transitional code checks for a warning, and if there is one, the next state will be the data logging state. Otherwise, the state shifts to time check. Suppose there is a warning and we go on to the data logging state. The current, maximum, minimum temperatures as well as the state of temperature warning is logged into a text file. The next state is a time check, which ensures that we are acquiring temperature every 0.2 seconds. There's no real functionality over here. However, the transitional code either sends the state back to acquisition or keeps the control in time check state. So, all in all, what happens here is that data is acquired in the acquisition and plotted on the graph, and then the temperature is compared with the upper and lower limits, and a warning could be generated. If a warning is generated, the warning along with the various temperatures are logged into a text file. If there is no warning generated, the state is time check, wherein it is ensured that the next sample is acquired within 0.2 seconds. With this example, I hope the concept of state machine is well understood. Further to the webcast, do participate in the contest of the week uploaded on the NI India community. On the NI India community, you can also watch the previous episodes of Webcast Wednesday. If you have some queries from the sessions or in general LabVIEW, you can get them resolved. You can interact with your peers and industry experts and get discounts on certification examinations. Also, if you attend 20 webcast sessions, you can win a free attempt to CLAD. Now, let's discuss last week's contest's result. There were a few interesting entries for the last week's quiz, but most of them had implemented the producer-consumer architecture correctly. However, what went wrong was sine wave generation. As you can see in the solution uploaded on the site, there are two producers and one consumer. In the producers, I have a sine wave Vi which generates a sine wave of 1 Hz. The top and the bottom producers have two sine wave Vi's which generate two sine waves of controllable amplitude. These sine waves are then given to an NQ element Vi. In the consumer, I have a DQ element which DQs the sine waves and plots it onto a waveform chart. Now, to see how this Vi runs, let's look at the solution. Here's how it runs if the amplitudes of both sine waves are equal. Now if I vary them, you can see the sine wave amplitude varying. Now, the content of this week is also uploaded onto the NI India community. The question is to create an ATM machine. There are no set conditions. You can assume a usual ATM machine and the usual inputs which a regular ATM has. NI is also conducting the Week of LabVIEW webcasts. This is an 8-part free webcast series to learn how LabVIEW can be used to build applications across various engineering and science disciplines. These are conducted on May 21st, 22nd, 23rd and 24th. So you might want to attend the webcast conducted on 23rd and 24th, that is tomorrow and day after. To register, please log on to india.ni.com/webcasts/week of LabVIEW.